The next set of two questions is based on the passage given here. Consider a block of conducting material of resistivity ρ shown in the figure. Current I enters at A and leaves from D. Okay, it is entering from here and leaving from D. We apply superposition principle to find voltage delta V developed between B and C. We have to find out potential difference across point B and C. Okay. Now the calculation is to be done in the following steps. Take current I entering from A and assume it to spread over a hemispherical surface in the block. Okay. So with this as the center, you assume that there is a hemispherical ball inside and current is spread across the surface of the hemispherical ball that we just assumed. Okay, we have to calculate electric field E at distance r from A. We have to assume that this A is the center of the hemispherical ball, and we have to find out the electric field E at a distance r from the center or from A. And we have to use Ohm's law, that is E equal to rho into J, where J is the current density, the current per unit area. Okay, from the R dependence of ER, obtain the potential VR at R. Okay, and then we have to repeat 1, 2 and 3 steps for current I leaving D to superimpose results from A and D. Okay, now the first problem based on this is that delta V measured between B and C is, okay, now let us say this is the surface with this is surface of the slab which is given. Current I is entering from above at point A, O is the center, and let us say this is the hemispherical surface that we are assuming of radius R. Okay, so current is leaving radially outward from the surface, hemispherical surface. So what is the total area of the hemispherical surface? It is 2 pi r square. So J, total current I entering, will leave from the total surface 2 pi r square. So J will be given by 2 pi I upon 2 pi r square. Okay, now electric field E is given by rho into J, which is rho I upon 2 pi 1 upon r square. Okay, now we know that potential difference delta V is given by negative integral of E dr. Okay, now the value of E is rho I upon 2 pi upon r square dr integral with a negative sign. So we will get rho I upon 2 pi, which is common, will come out, and integral of dr by r square. Okay, now this value is minus rho I upon 2 pi, and we will get minus 1 by r, the value of which is rho I upon 2 pi r. Okay, now we have to put the limits. Now from point B to C, if you assume one hemisphere of radius A, okay, and then you assume another hemisphere of radius A plus B, because this distance will be A plus B. Okay, this is A, this point is B, and similarly another hemisphere So this radius is A and this radius is A plus B. So we have to take the limits of R from A to A plus B. Okay, now if we substitute the values, we will get rho I upon 2 pi 1 upon A plus B minus 1 upon A, and if we calculate this, we will get the value as rho I upon 2 pi A plus B minus 1 upon A. Okay, now look at the options that are given. So the correct option is option C. Now the next question based on the above passage is, for current entering at A, the electric field at a distance r from A is, this we had just calculated, the value is rho I upon 2 pi r square. Okay,